So let's first introduce what a binary search tree is. So binary search tree, or BST, is a binary tree, first of all, due to the name, and you add to it three more properties. So first let me draw a binary tree in front of you. So 8, 1, 6. So what is so special about this binary tree that we see in front of us? Well, the first thing is that if we grab any node, let's say I'm at the root, well, the left subtree of this node should always contain keys, so values that you see in the left subtree. Those keys should be less than the node key, which is 8. So let's verify this. So 8, everything on the left of 8 is less than 8. So 1, 2, 5, 6, 7, all are less than 8. On top of that, everything on the right of 8 should be greater than 8. So 11, 15, 14. And that does not only apply to the root, it applies to any node. Okay? So, for instance, let me grab 2. Everything on the left of 2 is less than 2, and anything to the right of 2 is greater than 2. So those are two properties. With respect to any node, all keys to the left of node should be less than the value or the key in that node. Likewise, all keys to the right of the node should be greater than the value key in that node. So those are two properties. And the last property, which is trivial, is that the left and right subtree of any node must also be binary search tree. So that's like a recursive way of, maintaining that, all nodes should have the same property. I could have just said, oh, so the left subtree of the root should have keys less than the value of the root. And likewise, the right subtree of the root should have keys greater than the value of the root. Those are the first two properties. And then I can go ahead and say, all the nodes in the left and right subtrees are also binary search trees. So go back to 1 and 2. So each node now will serve as a root in a recursive way, right? So yeah, this is what a binary search tree is. That when you grab any node, all the keys to the left of that node are smaller than the node, and all the keys to the right of the node are greater than them. Okay, so now let's talk about how to search a BST. So given a BST, find a node with a given key. Simple as that. So let's say I have the following tree, which is a BST, and I'm asked to fetch or search a certain node with a given key, of course. Now to search a given key in a BST, we first compare the value, the desired value. Say I want to search 6, for example. So the question is how to fetch or find 6 in this BST. So an efficient way, of course you can do this exhaustively, there is no doubt about that, but you're wasting a lot of time. You need to exploit the structure of a BST, namely its properties, to search in the fastest way. We first compare the desired value, which is 6, first to the root. And if the key is the root, then we return the root, as simple as that. So if the 8 were a 6, then we just return the root, but it's not, it's an 8. Now if the key is greater than the root key, we have to go right and start searching here. So with this step, you have omitted, let's say, more or less, a great bunch of values, because we definitely know, due to the structure of the BST, that if the desired value is greater than the root, I don't have to search in the left subtree. So we've saved a lot of time. If you were to do that exhaustively, you would have gone first. So you would have first, due to the random guess, you would have started with the left subtree, which is not a good choice. And then, you would have done a search over there. You have wasted time if you did not acknowledge the BST structure. Now, since 6 is not greater than 8, it's not a good idea to go to the right, so you go left. And you do the same steps over and over again. So right now, in this tree, which definitely should contain 6, if it exists, of course, you repeat the same steps. So now 4 is the root, and do the same procedure over and over again. That is, 4. Is it equal to the desired value 6? No, it's not. Is it less? Yes. So the value 6 is contained in the right subtree of 4. So now this is the tree that you should be looking at. Again, you ask yourself the same question. Is 6 the desired value? Yes. So return this node. And that's it. Before we go into C++ and see how to implement the search method, let's talk about inserting to a BST, because that's how we're going to create the BST, by sequentially inserting nodes so that we have a BST to search. The question is, given a new node, given an incoming node, insert that node to a BST. So how do we do that? So a new key, you should always keep in mind that a new key is always inserted at the leaf. That is, go back here, and this is my tree right here. And I have a node that is, I don't know, 17. 17 should sit at the lower level, which is at the leaf of the tree. Let's say if I inserted 3, 3 should also sit at the leaf of the tree. So 3 would sit, let's see, so 3 is less than 8, so it should be in the left subtree of 8. 3 is now less than 4, should go to the left of 4. And 3 is greater than 2, so 3 should be sitting here. This is the 3. So what is the algorithm behind that? So we start searching a tree. Let's say I have the following tree. So 10, 2, 1, 3, and 50. And I'm asked to insert 4. So the algorithm behind the method insert should start searching a key from root till we hit a suitable leaf node. So once a leaf node is found, the new node is simply added as a child of the leaf node. So the method behind this is simply grab the root, which contains 10, and ask yourself the following question. Is the key 4 less than the value in the root, which is 10? Yes. So go left, go here. And now you are at 2. So 2 now is your root. And repeat the same procedure over and over again. So 4, is it less than 2? No. So go right. Now 3 is your new root. And ask yourself the question, is 3 less than the value? Yes. So go right and put your 4 over there. So now you could easily create a binary search tree using the insert method we talked about right now. And you can easily search a binary search tree using what we talked about here. Now let's do this on C++. So here I've got VS Code in front of me, and I've got the simple prototype, the usual include IO stream, and using namespace std and the int main. First thing is first, let's create a structure for the node, struct node. Of course, you can do this using classes. So each node of a BSD has a key, so value inside the node, and a pointer pointing to the left and to the right. So for that, now we could create a node as simple as saying struct node star root. Let's set it to null first and run. So as you can see, the console is empty, but no error so far. Okay, good. Now we need to insert to a certain node, right? For inserting, we need some basic abstract methods such as, let's say I want a function that creates a new PST node, new node, and I've got a key coming. First, let's instantiate a node. So struct node star10 is struct star node size of struct node. So this is the proper way of creating a pointer pointing towards a certain structure. Now the temp.key should be the key which we inputted. Now the left should be set to null. Also, right should be set to null. Now you could replace those 2 lines of code with a simple line of code as such. Left is equal to the right is equal to null. Simple as that. and just return the temp. So this is how you create a new node. Of course, we could have done this in the main, but we need to create a BST, so we need to call this method multiple times. Now let's insert. The insert method is going to return a pointer towards a node, right? Which is the node I'm going to, insert. I'm going to return a pointer towards that node, and I'm going to pass it as input the root. So the root defines the tree. So given the root, I can span the tree. Not only am I going to pass it the root, I'm also going to pass it the value I want to insert, the key I want to insert. So int key. Okay, good. So now, what's the logic that we should do? So let's write down some base cases. So if the node is null, just return a new node towards the key. So now the key is the root. Now else, if the tree is not empty, so then right here, empty BST and non-empty BST. So when you have a non-empty BST, if the key is less than your root.key, so if the key you want to insert is less than root.key, as we saw here, in case you want to insert a 4 and the root holds a value of 10, what should be done in this case? You should go left. So how do we translate this? You could do this recursively, right? So node.left, you call the function insert, but this time you pass it another root, which is the 2 in our case. So it is the root.left. So root.left, and the second argument should be the key you're inserting, right? So I still want to insert the same key. Nothing's changing in the recursion heap. Else, if the other case, if the key is greater than root.key, what do we do in this case? Same thing, we go right. So node.right is call the function to the right with the key. And finally, you would want to return your node. Okay, looks good. Let's try calling root equal insert root. Let's say I want to insert 10. So 10, run, and we have got an error. So here, this should be root. This guy should be root. This guy should be root. My bad. And finally, you would want to return the root. This is my bad. Run. So I have a small error, which is up here. We could remove structs, and we could just say new node. Simple as that. Run, and no error. So we have successfully inserted 10 as a root. Now let's insert other nodes. So let's insert 2. So root 2. Now let's insert 50. Insert root 50. Then let's insert 1 and 3. Insert 1 and insert 3. Right? Now we need a method to print the tree, right? So how do we do that? There's multiple ways to do that, as we talked about in previous lectures. There's many ways of printing a tree. I'm going to go for the in order. So if I go here and say void print in order. So normally you should pass it the root to identify the tree you want to print. And if your root is not null, so if it's not an empty tree, start printing. Now, in order is printing it in a recursive way. So you call print in order, and you go left. Printf, %d \n to go to a new line, and you print your key, right? Then you call the same method to the right. As you can see here in the previous lecture, we talked about 3 types of printing. So depth first traversals, you have 3 types of printing. In order, which is what we did, pre-order and post-order. So all this is in order. In order to what? It's in order to the root. So once you say in order, you're going to start printing everything on the left, then the root, then everything on the right. When you say pre-order, the root is first, then left, right. Post-order, vice versa. So root comes last, and in the beginning you have the left, right. So let's see how the tree looks like. Print in order and pass it the root. Run, 1, 2, 3, 10, 50. Then we remove the backslash n. 1, 2, 3, 10, and 50. So 1, 2, 3, 10, 50. So now we have successfully created a BST using the BST insertion method, and we've printed using the in order traversal way. So 1, 2, 3, 10, 50, 1, 2, 3, 10, and 50. Okay, so now let's see how to search. So what we talked about over here. Right here we were searching the key 6, right? So what did we do? We first started with the root. If the value we're looking for is less than the value in the root, go left and repeat the same procedure, but this time the root is 4, right? Until you hit the desired value. How do we translate that into C++? So I'd like to return a structure, or more formally a pointer towards a structure, a node. I want to pass it the root of the tree that I would like to fetch a certain key, and the key. If the root is null, meaning that we have an empty tree, just return the root. This also happens when you hit. So when you found the key, meaning that the key of the root is equal to the desired key, return the root, because that's the node that contains the key we're looking for. Else, if, let's go back here, if the key right here contains a value less than the root, go left. How do we do that? Recursively, if root dot key, which is 8, is greater than 6, so greater than the desired key, return, call the method, but this time you go left. So root dot left with the desired key. Else, if we're not at the base case right here, and if we're not in this scenario, meaning that our desired key is greater than 8, let's say we're looking for a 9, for example. So the only choice we have is to go right. So right here, return search root dot right of the key. Okay? How do we make sure the following is working? So let's go right here and let's try to search a certain node. So struct node to fetch is a node, right? It's also pointed to a node. Let's pass it the root, which is the root. And the key, let's say I'm looking for 3. I would want to print, let me do a cout right here, node to fetch, dot key. Here we have the 3. Let me just replace it with the cout, root dot key, run, so that we print each on a line. So this 3 right here is due to this printing. So let me do this, node to fetch has value 3. There you have it. Now let's talk about how to delete from a BST. So say I've got the following BST and I'm asked to delete a certain node. Well, for deleting a node, we have 3 possible cases. Case 1 is when the node that we have to delete is a leaf node, meaning that it has no children. For example, 2, 4, 6, and 8. Possibility 2 is when the node to be deleted has only 1 child. Unfortunately, in this tree, we don't have such a node, but let's say I'm in this situation. Well, 3 is a node with 1 child, right? And the last case is when the node to be deleted has 2 children. Such cases in this tree are clearly 5, 3, and 7. So let's tackle each case separately. So let's say I want to delete a leaf node. How do we delete it from a tree? We simply remove it, and no modification in the tree is further needed. So let's say I want to delete 4. All I have to do is this, and that's it. It reserves the properties of the BST, meaning that everything on the left of any node, it contains keys smaller than that node. Likewise, everything on the right of a node contains keys greater than the node. Now let's say I want to delete 3. What do? So I'm in this case right now, we're deleting a node that has 1 child. So all I have to do is copy the child to the node and delete the child. That being said, I copy 2 to 3, then delete 2. So the 3 becomes a 2, and then I delete the 2 as such. Easy, right? Now last but not least, which is the most complicated, not too complicated, but it's the most complicated between all cases, is when you want to delete a node with 2 children. In that case, let's say I want to delete 5. What do? Well, in this case, we need to first write down or figure out the in-order sequence of the tree. So if I were to print this tree in order, I will have first 2, then 5, then back here. So here we repeat the same process. 6, then 7, and last but not least 8. So if I were to delete 5, which has 2 children, I will delete it in the following sequence. So 5 right here goes away. Then I will end up with a BST that has the following in order: 2, 6, 7, and 8. Now, how is this reflected onto the tree? This means that you first have to find an in-order successor of the node. So what is the in-order successor of 5? It's 6. Then you copy the contents of the in-order successor, which is 6, to the node, which is 5, and delete the in-order successor. That being said, all this subtree is copied here, or takes the place of 5, if you will. So the tree will be something like this. So instead of my 5, I will have 6 right here, and down here I'll have a 7 and the 8, right? So now if you will print this tree in order, you'll have 2, 6, 7, 8 as this sequence. Now let's implement the delete method in C++. So I'll return a node that will replace the node to be deleted. I'll pass it the root of the tree and the key to be deleted. So let's first start with the base cases. If my root is empty, could be because we didn't find the key to delete. If I were to write this function recursively, I will reach a null in case I didn't find the key. So in that case, I will return the root or null. So this base case happens. Now, if key is less than root dot key, right, then go left. So how do we translate that to C++ terms? So the key is less than root dot key. Simply root dot left. We call the method again, so recursively onto root dot left and pass it the key to be deleted. Likewise, if the key I'm looking for is greater than root dot key, go right. So translating this, we call the function recursively. So this guy right here is an else if. And finally, else. Now right here, what happens? If we found the key, if we hit a certain node with the same key, now is the time to argue the following cases. Let's organize here. If node with no children, node with 1 child, and node with 2 children, right? What do we do in case we don't have children? So if root, how do we check? If root dot left is null and root dot right is null, actually we can tackle both in the same case if you have no children or one child. So right here I'm going to keep root.left is null and argue here if root.right is null. This works for both cases. So what happens if the left is null? So I'm going to create a temp and go right. That's one. And I'm going to free the node I am at the moment. So free it from memory and return the temp. Likewise, if the right is null, I'm going to do the same process. So I'll copy paste all this right here. This time I'm going to point at the left. So in that case, what would I have done? I would have only freed the node to be deleted from memory. That's what I want to do. I want to remove it from the tree. Now, when the node has two children, I would want to get the in-order successor of root, right? So how do we do that? If we look back here in the sequence, it is the number that comes directly after 5 in the tree. So it is the minimum value of the node in the right tree with respect to the node I want to delete, which in my case here is 5. So in other words, I would want to return the min value of tree. So min value of tree, which has a root.right with respect to the root I'm deleting. So in other words, the tree has root 7, right? And 7 is the right of the node I want to delete, which is 5. So that's why I'm passing root.right. And it's yelling at me here and it's telling me it's undefined, min value of tree. That's because I didn't implement it. So we go back here and we create a function designed to get the minimum value in a tree. Simple as that. Because I am passing root.right. So given a tree, get the minimum value. How do I do that? It's really easy. So I'll return a node. So struct star node temp is the root. Return temp. And we're going to do a loop here that does the following. So while temp.left is not null, keep going left. Temp is temp.left. Because I know the minimum value is always to the left. This is a BST, right? So always go left. I also want to condition over temp not being null. So this function right here, given a certain root, it keeps going left to choose the minimum, which is what I want. And now that I found the in-order successor, all I have to do is copy the in-order successor contents, to be more precise, to this node. So how do we do that? It's as simple as root.key. So the key is replaced by the temp.key. So the temp right here is holding a key that should sit in the root. That is, the temp will hold the value 6 because it's the minimum in the right subtree, and then it should sit in the root.key, which is 5. So 6 will sit here. And then finally, what do we do? We should delete the in-order successor. That is root.right, delete node, which is the function itself. So we do that recursively, but this time on root.right and on temp.key, right? Finally, you'd want to return your root. Now let's go down to the main, give it a shot. So if I remove this right here and I run, this is what I had from stdio.h. Run, free is not working. Move stdlib. There you go, it works. Make sure stdlib is included because free method is found in this library. So this is the tree that we had, 1, 2, 3, 10, 50. So going back here, yeah. Let's say I want to delete 1. So go down here, delete node, passing the root at 1. And let's do the printing after the deleting. Run. And there you have it. 1 does not exist. Now the tree looks like this, right? So let's try to delete 2, which has 1 child. So delete 1 and 2. There you have it, 3, 10, 50. So the tree looks like this. And now let's delete 10 and run 3 and 50. So the tree looks like this right now. So 3 is here because we deleted 2. So the 3 is here. And if we delete 10, we end up with 3 and 50 on the root, which is what we have here. Okay? So that's about it. That's the basics of binary search trees. That's all you need to know to start implementing methods that include binary search trees. I'll see you in the next one.